Now, if I'm using prime factorization for perfect squares, a perfect square is any number that is equivalent to two whole numbers multiplied by themselves. So if I'm looking at perfect square whole numbers, they are 1, 4, 16, 25, 36, 49. 1 would be 1 times 1, 4 is 2 times 2, 16 is 3 times 3, sorry, 9 is 3 times 3, 16 is 4 times 4, and going on. Every perfect square has two square roots, the positive version and the negative version, which means that I could get 4 from 2 times 2, or I could get it from negative 2 times negative 2, which is going to be an important principle once we get to grade 11. The ones that we're dealing with are going to be the principal square root, which is just the positive version. So if we're trying to address whether or not a number is a square root, if it is two whole numbers, or a principal square root, if it is two whole numbers that are multiplied by themselves, then the prime factorization should always be symmetrical. If I'm looking at 9, 9 splits up into 3 times 3, where I can see that I have an exact pair of two of the same number that's multiplied together. If I have 36, that could be 4 times 6, and this would be 2 times 2, and 3 times 3. Which means that, once again, I can see that here's a pair of 2's, and here's a pair of 3's. If I took 49, that is just 7 times 7, which means that there's just two 7's. If I took 64, then 64 is the same as 4 times 16. This would be 2 times 2. This would be 4 times 4. And these would be 2 times 2 and 2 times 2. So this is actually 2 times 2 times 2 times 2 times 2 times 2. I have one pair of 2's, two pairs of 2's, three pairs of 2's. If I'm looking for the square root of any of these numbers, I just take 1 from each set. So here I just have one set, 3 times 3, so the square root is going to be 3. For 36, I take 1 from each set. There's a set of 2's, so I take 1, 2. There's a set of 3's, so I take 1, 3. And it's going to be 2 times 3, or 6. There's only one set for 7, or for 49, so it's just going to be 7. And there's 3 sets of 2's for 64, so I take 1 from each of the 3 sets of 2's, and 2 times 2 times 2 gives me 8. If any prime factorization gives us a perfect square, it means that every single prime number exists in sets of 2 with no prime numbers left over. If I'm considering the number 44,100, then if I want to see if it is perfect square, then all I have to do is I'm going to factor it into prime factors, and group the factors in sets of 2 with no remaining. when I factor down 44,100, then its prime factorization, I get 2 times 2 times 3 times 3 times 5 times 5 times 7 times 7. And I can see that I have a set of 2s, a set of 3s, a set of 5s, a set of 7s, and none left over. Which means that the square root of 44,100 is going to be a 2 times a 3 times a 5 times a 7, one from each set, and that's going to give me 210. So 210 times 210 is the same as 44,100. If I'm following this principle and I want to double check if numbers are perfect squares, or prove that they're perfect squares, then I'm just going to factor it down. I can't factor this by 2, but I can factor it by 5. Divide it by 5 again, and I get 49. And this splits up into 7 and 7. I group the prime numbers, and there is none left over, so it is a perfect square. And then it's asking me to state the square root. Well, the square root of 1225 is the same as 1 from the first set of 5s, 1 from the set of 7s, or 35. If I'm doing the same thing for 3042, then I'm going to say that this is going to be 2 and 1,521. I can't divide it by 2 again, which means that there's only going to be one 2, and at this point I could actually just say that it is not a perfect square. As soon as I have to jump to the next point, and now I'm going to have to divide this by 3 instead, I can tell right away it's not going to work. If I'm doing the same principle with cubes, well, a perfect cube is the same number multiplied 3 times, which means logically, if a perfect square is when I have 2 times, and I need all the prime numbers to be in sets of 2s, then for 3s, it needs to be in groups of 3. So if I have 27, that's the same as 3 and 9, and this is going to be 3 and 3. And I can see that I can group this off into 3 of the same prime number with none remaining. If I'm doing 216, then I could say that this would be 2 and 108, which would be 2 and 54, 2 and 27, 2 and 9, and, 3 and 9, and 3 and 3. There's my set of 2s, there's my set of 3s, and I don't have any remaining, so it is perfect. If I'm doing the same thing for 3,375, then I'm going to say that this is going to be 3 and 1125, which goes to 3 and 375, which goes to 3 and 125, 5 and 25, and 5 and 5. I have 3 3s, I have 3 5s, and I have nothing left over. So, if I am using prime factorization to prove that something is a perfect cube, then I need to make sure that it breaks into groups of 3 of the same prime factors with no remainder. So, if I'm taking 6,912 and that's going to give me 2 and 3, 4, 5, 6, 2 and 1,728, 2 and 864, 2 and 432, 2 and 216, 2 and 108, 2 and 54, 2 and 27, 3 and 9, 3 and 3. I have 1 set of 2s, 2 sets of 2s, 2 2s that do not make a set of 3, and 3 3s. Because I have 2 remaining 2s that don't fit in a set of 3, this is not a perfect cube. If I'm trying the same process with 970,299, I can say that this splits into 3 and 3 2 3 4 3 3. This is 3 and 107 3 1 811. This is going to be 3 and 3 5 9 3 7. 3 and 1 1 9 7 9. 3 and 3 9 9 3. And 3 and 1 3 3 1. Can't divide by 3 anymore. Can't divide by 5. Can't divide by 7. And I get to 11 and 121. And 11 and 11. I have 1 set of 3s. I have 2 sets of 3s and all my 3s are gone. And I have 1 set of 11s and all my 11s are gone. This is a perfect cube. If it needs me to state the cube root of the number, then the cube root of 970,299 is going to be equal to one of the 3s times another 3 times an 11, or 99. And that's it.